Start starting. We talked about robotic system design. We talked about Bayesian filtering. Today, we're going to try and instantiate Bayesian filtering in a way that you all can implement on the car. And then we'll start talking about some methods to make Bayesian filtering tractable. So specifically, we'll talk about the particle filter. Right? So some logistics. You all should be underway in project one. You on Jan 21st, which I think is Tuesday. And then we'll release project two same day. Right? And so project two is actually on the car. And so you'll have some fun with the hardware. So any other logistical concerns? Homework one has been okay. No troubles. Lab access, picking up the cars is okay. Yeah. Okay. Good. Let's start with our little participation quiz. The question is, what is a motion model? We have xt plus 1 given xt in ut. We have xt plus 1 given ut. Zt given xt. Zt plus 1 given z. Give it 10 more seconds. Everyone got it? Yeah. Okay. Let's keep going. So start with a little recap. We've been talking about Bayesian filtering. Bayesian filtering is the process of getting probability of xt given u1 to t, z1 to t. We're trying to come up with a recursive process that connects the previous belief with the measurement model and the dynamics model, right? So the dynamics model is a one-step model, saying xt minus 1, ut minus 1, and telling you the likelihood of xt. So it's like telling you how the world will move in one step. And the measurement model would be of zt given xt. So it's telling you what is the likelihood of a measurement from your sensor given you at some particular state. Right? And so we worked this out earlier, but a Bayesian filter has two steps. A prediction step, which takes the previous belief, pushes it forward to the motion model, to the dynamics model. So it says, take your previous belief, multiply times your dynamics model, sum it up over all the previous states. And your correction model, which uses Bayes' rule. So it takes your belief at different states, weights it by the likelihood that the measurement that you got happened from a particular state, and then normalizes. Okay? Prediction, correction. So that's basically the recap. We went through some examples. And today what we're going to try and do is try and define what is our motion model and what is our measurement model for the car and the LiDAR, right? And that'll allow us to start implementing things on the hardware. So we've been talking about motion models for the prediction step and the correction step. So the motion model kind of needs to figure out what is the next state given the previous state and a control. So control is ut, previous state is xt minus 1. We're just going to use physics to get this, right? So we're just going to do a little bit of physics. So really what we want to specify is what is the derivative, the time derivative of the state given the previous state and the action, right? So we're trying to say like, what is dx dt given previous state and action, right? Or given your, or instantaneously given your state and your action, what is the derivative of state? And if you know the derivative of state, you can get the next state by like integrating it over time, right? And so basically, if you know how the state is changing instantaneously, you can integrate it over time to get the next state. So you can kind of think of a motion model, which we're going to treat as a discrete model, as something that kind of integrates this the instantaneous derivative of state with respect to time, right? So given a control and the current state, what is dx dt? That's what our motion model is going to be. Right? So we're just going to use physics to try and derive dx dt, and then we're going to integrate it to give us the next state. So our x is going to be x, y, and theta. Right? Our state is going to be a vector of the x coordinate, the y coordinate, and the heading. So like, what is the angle that your car is facing? Your actions are going to be velocity and steering angle. And so you're going to be able to control things like your throttle, and you can control your steering angle. Right? So that's our system. And given this x dot, we're going to try and compute what is delta x, delta y, and delta theta by integrating x dot, right? with on some time interval. It'll give me a change in x, change in y, change in theta, and that'll give me my next x, y, and theta. Right? So we get the instantaneous instantaneous rate of change of the state. You integrate that to get delta x, delta y, delta theta over some small delta t. And then you add some noise to it in order to make it probabilistic, right? So you can kind of think of this intuitively as your car is facing some direction. You apply some velocity, you apply some steering, it goes somewhere else. Let's say it goes over here, and then you're going to add some noise to it. So you're going to give it some uncertainty, right? And so we're first going to try and work out, we're first going to try and specify what f is using physics. We're going to do some integration to get what the next state is going to be. Then we're going to add some noise to get uncertainty. Right? So the motion model is going to be physics, integration, uncertainty. Yeah. Questions? Good. All right. So the first thing we need to define is this thing called the instantaneous center of rotation. Folks heard about this? Anyone hands up if you've heard about this? Okay, so the idea behind instantaneous center of rotation is imagine you have a rigid body that is both translating and rotating. Right? So it's like, let's say it's translating and rotating, right? So a body is moving like that. You can think of in a combination of a translation and a rotation as a rotation about a different point. So you can kind of think of a combination of translation and rotation as a pure rotation about a particular center, right? So you can kind of think of it as like, try to think of this as a plate, right? And think of this as the center of your plate, and this thing just lies on your plate, right? So it's like, imagine this is like a disc, and the disc is rotating around this center over here, right? So you can kind of think of like, it's a pure rotation around this guy, but from the perspective of this body, it is going to translate some and it's going to rotate some. And so from the perspective of this body, like moving like this, where you translate some and you rotate some, is a pure rotation around a different point, which might lie outside the body, right? And so you can always write a combination of a translation and a rotation for a rigid body as pure rotation around a different point, which may not be inside the body, right? So for this L shape, for instance, it doesn't lie inside the body. It's like somewhere else. Does this kind of make sense? Right? So you want to think of this as like a pure rotation. So you want to think of the instantaneous center as being something that if you like, you can kind of think of it as the center of the disk, which makes like the translation and rotation. How do I put it? It's like the center of the disk for which this translation plus rotation looks like pure rotation. Right? And so the way you kind of find your instantaneous center of rotation is you take the velocity at different points in your body, right? So like, let's say the velocity was going this way here. The velocity at this point was going this way. This point is going this way. You know that in a pure rotation, the velocity is perpendicular to a line from the center, like in a circle, right? Let's say a circle is rotating. You know velocity is going this way. You know that the radius is perpendicular to a tangent, right? So in a circle, you know the radius is perpendicular to a tangent. And so you take the velocities, you draw something perpendicular to the velocities, and then you see what point it intersects at, right? So then you can say that this is basically a pure rotation around that point because these things serve as like tangents, right? So the way to find the instantaneous center of rotation is take the velocity at different points, draw perpendiculars, and see where they intersect. And that gives you the instantaneous center of rotation. And it's going to be much easier for us to deal with rotations than combinations of translations and rotations. Right? So the reason we're going to do this is so we can determine our kinematic model. But the idea is just always draw perpendiculars to your velocities, see where they intersect. That is the instantaneous center. Does that make sense? If you want, just Wikipedia, it has a nice article. Good. All right. So now we want to do things with our car, right? So we want to do things with our car. And so we're first going to try and find, we're going to define everything in terms of our car. And we're going to then try and find the instantaneous center of rotation, right? So for instance, we're going to define a few entities. We are going to define, let me see if I actually mark these things. Okay, so we're going to define, for instance, the position of the car on the X, let's call this our X-axis, our Y-axis, right? And the X and Y, let's take our rear axle as our reference point. So X and Y is going to be the position of the center of our rear axle, right? So the first assumption we're going to make is that a four-wheel car is going to behave like a bicycle. So it's often called the kinematic bicycle model. And that's because like the wheels, we assume the wheels don't have slip and these kinds of things. And so we assume that everything is rigid, the wheels don't have slip. So we're going to essentially pretend that it's a bicycle. Yeah. And so first thing we're going to do is we're going to say the velocity of the system is going to be defined as how the point at the middle of the rear axle moves. Right? So it's going to move in this direction. So this is going to be the vector v. And what we want to determine is x dot, y dot, theta dot, which is dx dt, dy dt, d theta dt. Yeah. So given the velocity of the system is moving this way, what is dx dt going to be? And theta is the angle with respect to the x-axis. Let's not worry about the steering angle for now. Theta is just the way the car is facing. Right? So what is dx dt going to be? What is x dot? Theta velocity, so the x component of the velocity. That's right. It's going to be the x component of the velocity, which is going to be v cosine theta. Right? Similarly, the y direction is going to be v sine theta. Right? This is just like trigonometry. Like this is v. So the x component is going to be v cosine theta. The y component is going to be v sine theta. Right? This makes sense? Just think about projecting the velocity along the axes. Okay, so the first two things we're going to say is x dot, which is dx dt, is v cosine theta. And y dot, which is dy dt, is v sine theta. Okay, so those are two things for x and y. Theta is going to be a little more difficult, right? So whenever you have a rotating system, right, you can always say that theta is going to be equal to, or theta dot, right, which is like how much the heading is changing, is going to be equal to the angular velocity of your system. It's going to be equal to the angular velocity around the center, the instantaneous center. And the angular velocity is going to be defined as the velocity divided by the radius. So if you remember high school physics, your velocity is equal to r omega. Your torque is equal to I alpha, and your velocity is equal to r omega, right? And so your velocity is equal to r omega, which means your omega, which is how much the heading is changing, is v divided by r. Yeah. So this is just from like the definition of angular momentum, yeah, or angular velocity. R is the distance between, it's like the radius of that instantaneous circle. So it's the distance between our point and the instantaneous center, right? So that is, this is what we're going to define as R. And we're going to say that like the velocity of this point is V. And so the angular velocity of this thing is going to be V divided by R, where R is the distance between this point and the instantaneous center, which we haven't figured out yet. We don't know what it is, right? But if we knew R, then the change in theta is going to be V divided by R, right? And the way you get it is just V is equal to R omega. Omega is equal to V divided by R. If I knew this distance, I know V, I know, if I know R, then I can get omega, right? So what we're going to try and do is figure out what is R. Yeah. Okay. Does it make sense so far? Theta dot is omega. Omega is V over R. We need to figure out R. Okay. So to figure out R, we're going to do a little bit of geometry, right? So we're going to say that the length of the car is L. So the length between the rear axle and the front axle is L. The distance from the rear axle to the center is R. And the steering angle is going to be delta, right? The angle that your wheels turn is going to be delta. Yes? And as I said before, the wheels don't slip. So this is going to go this way. This is going to go this way. So if I look at the instantaneous center, I have to draw a perpendicular line this way. So this is a right angle. And I have to draw a perpendicular line this way, right? And this is a right angle. To get the instantaneous center, you take 2 points, take their velocities, you draw two right angles, right? You see where they intersect, which means that this is a right angle right here, and this is a right angle right here. Yes? So just by the definition of the instantaneous center, draw a right angle here, you draw a right angle here, you see where they intersect. Right? So that just helps us define a triangle. And our triangle is going to be, this is going to be delta, which is your steering angle. This is going to be 90. So what is this angle going to be? So remember, this is a straight line. This is delta. This is 90. What is this guy going to be? What is the remaining? 90 minus delta, right? So this is going to be 90 minus delta, right? So just like, sorry, my handwriting's a little rough, but it's delta, 90 degrees, 90 minus delta. So they sum up to 180, right? And so that's going to be 90 minus delta. And this is a right angle right here. So what is this angle going to be? Remember, this is 90 minus delta. This is 90. What is this angle? Delta, right? Okay, so now we've kind of worked out our triangle. This thing is delta. This thing is 90 minus delta. So now given this angle, what is R? Like, can I express R in terms of things that I know? What I know is delta and I know L. How do I express R in terms of delta and L? Yeah.
You have two side lines of the right.
That's right. That's right. Perfect. So we have two sides of a right triangle. So you know the tangent. So you know this thing is delta. And you know that tangent delta is equal to opposite divided by adjacent, right? So it's going to be L divided by R. So tangent delta is L divided by R. So what is R? Okay, I guess I wrote it on here. The effect wasn't what I expected. So R is going to be L divided by tangent delta, right? And so now what you've done is you know the length of the car, you know the steering angle, and so you can write the distance between the back axle and the center of rotation in terms of things that you know. Right? So now R is going to be L divided by tangent delta. So what is theta dot going to be? Can we simplify theta dot? Be tangent delta divided by L. That's right. Yeah. V tangent delta divided by L. Okay. So let's just recap if you want to, derive these things. All you're going to remember the instantaneous center of rotation is you take 2 points, look at their velocities. The 2 points you're going to choose are the rear axle and the middle of the front wheels. The car doesn't slip, so the front wheels move exactly in the direction of the steering angle, and the rear wheels move directly in the direction of the velocity. Right? So the rear axle moves this way, the front wheels move this way. So when you draw the right angles, they meet at the instantaneous center of rotation, right? And so you're just going to work out your geometry by drawing these perpendiculars and just doing a little bit of 90 minus delta, right? But the point is that you really want to express the instantaneous center of rotation, the radius R, in terms of things that you know, which is V, delta, and L. Right? So now you've taken dx dt, right? Dx dt, if x is the state, is basically, it's dx dt, dy dt, d theta dt. And you've written in terms of things that you know, V cosine theta, V sine theta, V tangent delta by L. You know this, you know this, you know this, you know this, you know this. You know everything, right? So you have like a fully defined model, no unknown quantities. Yeah. Okay, good. So that is all that the kinematic bicycle model is. And if you look at like a lot of the more complicated systems out there, they're not actually that far off from the kinematic bicycle model. So if you look at, for instance, the DARPA racer vehicle, like it uses a slight modification of the kinematic bicycle model underneath. And so it's very simple geometry that underlies lots of these complex systems. You have to add some things for slip and these kinds of things. Okay, everyone with me on how do we get dx dt? Right, this is how you specify your model. Now we just need to integrate it. Right? So we're going to try and integrate it. We're going to try and integrate it numerically. So we're going to try and we're going to take like x dot, and we're going to try and integrate it. We're going to take y dot, we're going to try and integrate it, and theta dot, we're going to try and integrate it over some like t to t plus delta t, right? So we're going to try and like say over some period of time, we want to integrate what is our change in x, what is our change in y, what is our change in theta. And so you're going to try and change from t to delta t, t to t plus delta t. So you have some time step that you choose as your discretization. You're going to try and integrate these in order to like get what the next state is going to be. Okay, so let's do a little bit of integration. So we want to get delta x as the integral of x dot dt between t and t prime, where t prime is just t plus delta t. Yeah. And so we're going to try and integrate x dot, but x dot is v cosine theta, right? You want to integrate v cosine theta dt over time from t to delta t, or t to t plus delta t. Now, the tricky part about this is that your v is a constant for that time, but your theta might be changing, right? So your theta is changing over time, right? And so theta is a function of t, and it's a somewhat complicated function of t. And so this integral is kind of hard to compute. So what we're going to try and do is we're going to try and convert this integral in terms of dt to an integral in terms of d theta. Okay, and it's going to be easier to compute. So all we're going to do is we're going to multiply and divide by d theta over dt. So theta dot is equal to d theta over dt. Okay, theta dot is just, whenever you have a dot, it's just a derivative with respect to time. Okay, so theta dot is just d theta over dt. We're going to multiply and divide by theta dot. Yeah, like nothing changed. We just multiplied and divided. Then what we're going to do is we're going to cancel out dt, right? And so then you can write your expression as v cosine theta d theta divided by theta dot. Let's actually take one step before we get here. We can write your expression as v cosine theta divided by theta dot d theta. Yes? And so the assumption we're going to make, which holds reasonably well in practice, is that your steering angle, like the change in steering angle is constant between t and t prime. Or your steering angle is constant, which means your change in heading, the rate of change of heading is constant between t and t prime. So that's the assumption we're going to make. And that's going to make theta dot constant. Right? So we're not going to say that theta is constant. We're going to say the rate of change of theta is constant. Okay? And so what that's going to allow us to do is going to allow us to take theta dot and v outside of your integral. So it's going to be v over theta dot integral cosine theta d theta. Okay? And now what is integral cosine theta? You remember? Sine theta? Yeah. Good enough guess. Yeah. It is sine theta. Nice. And so the way you integrate delta x is that you're going to say multiply divided by theta dot. The assumption is that the rate of change of theta remains consistent because we're going to assume that our steering angle doesn't change over that small interval. And so if your steering angle doesn't change, we're going to assume that the rate of change of theta remains the same. And so we're going to like integrate with respect to theta, and that's going to be sine theta prime minus sine theta. Right? So if you want to get the change in x, you look at v over theta prime, and you integrate with respect to cosine, you get sine. And then you can simplify this by noting that theta dot from our previous slide was v tan delta over L. Right? We derived this earlier for theta dot. Right? So we're saying that theta dot is v tan delta over L. We're assuming that the steering angle is constant, which means that theta dot is constant. Right? So if delta is constant, that means theta dot is constant. Right? And then you do that to take v over theta dot outside of the integral. And this allows you to derive delta x. Okay. Yes, no, maybe, confused? Yeah. Yes. So the rate of change of theta is constant, but theta is not constant. Yeah, or like the velocity is constant. Like, so we're saying that the velocity is constant, but we're not saying that the angle is constant, right? So the way to see why theta dot is constant is we're saying that the steering angle is constant, and theta dot is v tangent delta over L. We're saying v is constant, delta is constant, L is constant, which means theta dot is constant. But that doesn't mean theta is constant, right? Like it's changing. Okay, so the way we work it out is multiply and divide. Note that steering angle is constant means theta dot is constant. Take those things out, integrate. That's it, right? So that gives you delta x. Yes. Theta becomes theta. Because you don't have the presentation of like t cosine theta. And in the second one, you have like t cosine theta. Oh, I guess theta of t just means theta, which is a function. Okay. So just it's like shorthanding because we're saying that like that the only reason to say theta of t in the first integral is to say that theta is a function of t, which is like a kind of complicated function. But I guess in the second one, if you're in terms of theta, it's in terms of theta. So its dependence on t is irrelevant to that. Okay, so remember, you just want to get the integral in terms of t, in terms of to an integral in terms of theta, multiply, divide. Note that theta dot is constant. That's it. Okay, so you can do the same thing for delta y, right? You just like, you're going to replace the cosine over there with the sine, and the integral of sine is going to be negative cosine, right? And so that's going to give you the second term, right? So the only difference, remember, it's a little careful, a little tricky that the signs are flipped between these, right? Just remember that. So it's going to be exactly the same derivation. This guy is just going to be sine, right? So you're going to use all the same logic. And then the last one is going to be what is delta theta, right? And delta theta is just going to be integral theta dot dt. Theta dot is v over L tangent delta. We assume that we assume delta was constant, so all of that comes out. That's just going to be integral v tangent delta over L dt. All of this comes out, which means it's just v tangent delta over L delta t. That's it, right? So this one is the easiest one, right? So which means that you just take v tangent delta over L times delta t. That tells you what delta theta is, right? And once you know delta theta, you can compute what theta prime is. Theta prime is just theta plus delta theta. And once you know theta prime, you can compute this guy, you can compute this guy. Yeah. So you don't need to derive this over and over. It's just nice to know how to do it. You want to just convert your integrals into things that are easy to do. Any questions?
Does this have like better like modeling as compared to like using Euler's method?
This is Euler's method.
Oh,
This is Euler's method. Yeah. So you're just saying like you're going to take, you have like you're just discretizing, and your Euler's method would just say you take your previous thing plus derivative times delta t, right? So you're just integrating over. Yeah. Okay. Questions?
yes, if the change in steering wheel was not constant, let's say you're following with an S curve or something, this becomes significantly more difficult.
Yes. Yes. So often what you'll do is you'll try to convert it into a small enough thing where you can have those assumptions hold.
Like
Right.
really small.
Yeah, exactly. Other questions? Make sense? So the resulting updates basically look like theta t is theta t minus 1 plus delta theta. Delta theta was v over L tangent delta times delta t, right? We computed what delta x was, we computed what delta y was. You can get the next state by taking the previous state and just adding delta theta, delta x, delta y. Okay, so now we've done the first step of our motion model. We've taken previous state and we've computed what the next state is going to be, right? The next thing you need to do is you just need to add some noise, make it probabilistic. So all we're going to do Let's skip through this. All we're going to do is we're going to try and make our model probabilistic. So we just want to say, add some noise to the model right after you kind of step through it. And so typically what you'll do is you'll just add some Gaussian noise after you do the step, right? So you say, I'm going to like integrate with this step, and I'm going to add some Gaussian noise around this deterministic step. So you're going to take a deterministic step, and then you're going to add some Gaussian noise around it. Right? So it's saying that there's some uncertainty there. Yeah. Zero, right? So that would be like and zero is over like yeah, if happens if n delta was zero, right? Then you would have and delta is tan zero is zero. Yep. So if you have b divided by zero, you don't divide by that, you divide by like, oh, I see. I guess you probably get a like I think of it like numerically it would be a 0 by 0. Like the theta wouldn't change, the numerator will also be 0. So I think those would be like just a 1. Oh, okay.
What if the tan and the cosines cancel out then? Like, and then it wouldn't be fine, right?
Yeah, exactly. That's what I'm saying. So it's like if this is let's kind of go to our slide. Yeah, so Davin's question was if this is 0, okay, then theta doesn't change. If theta doesn't change, then this is 0 and this is also 0. And so then these would just cancel out to 1, right? Yeah. And so, yeah. So the point is that you would kind of like, you wouldn't worry about that so much, right? Okay, got it. Yeah.
We have to apply this to every single possible state that we're in.
We have to apply this to every possible state like this.
Since our first state is a belief.
Yeah, so when you talk about particle filter next, but the way you often implement these things is you have a set of particles which represent the belief of where you might be. And for each of those, given one control, you have to run this in support. So the nice thing about this is like a really cheap operation. You can run it. And often like if you're doing things with the GPU, you'll run it forward in batch and make it faster. Okay, so what we've done so far is define our motion model. Our motion model is basically, see if I can summarize it. Our motion model is we're going to integrate, and the integral is just like these computations. And then you're just going to add a bit of noise, which is typically Gaussian noise around your integration, right? And that is going to be your motion model. As Marco was saying earlier, you have to run this forward for every previous state that you're trying to propagate forward. We'll see how to do that explicitly, but in the discrete version, you have to do it for every single version, every single xt minus 1. Okay, so that's motion models, right? So that's the car motion model we're going to do. It's clearly a simplified model, but it works pretty well when you're going at slow speeds. Questions? You good? Yes.
On the fly while the robots.
Yes. Yes. So the nice part about these calculations is that they're like relatively simple. Like they're like closed form in that, okay, you like implement the first guy. It's just one tangent operation, some multiplications and divisions, right? And you don't have to do any like huge matrix multiplies or anything. And so it's like pretty fast. So, yeah, tends to be okay. It gets harder as your state gets bigger. Yeah. Question?
So, yes, regarding adding noise to the.
Yeah.
So,
Yeah.
Is that just because you want to expand like the state space so that when we do consider all the possibilities, like we just take the one that actually has the best measurement?
Okay, so the question is, why do we add noise, right? And so the reason you add noise is because we made a bunch, like this whole process, we made a bunch of assumptions, right? For instance, we said delta is going to be consistent and theta dot is going to be consistent. And we made like this no slip assumption, right? Like those are not actually correct. Like that's not how a real system works. And so the noise is to account for the fact that those things aren't perfectly correct. And so you have to like account for possibilities that you might actually be in a bigger range. Right? And so it's to deal with the fact that your model is making assumptions. Okay, so that is motion models. We'll implement motion models in homework 2. Pretty much just you can copy paste these slides and they should in NumPy, right? But the next thing we need to do is we need to, as we define a motion model, we also need to define a sensor model. So we need to do prediction, correction, prediction, correction. And so we need to get P of ZT given XT, right? So we're going to use a LiDAR, right? So we're going to use, it's called Y LiDAR, but commercial LiDARs like Velodyne kind of work by shooting out laser beams. Right, so they have lots of different directions. You shoot out laser beams, and then you see, you'd like see how long it takes for the laser beam to come back. So you hit something, and you see how long it takes for the light to come back, and you measure the time, and that gives you like distance, right? This is certainly an advertisement, but like Velodyne lasers are Velodyne lidars are pretty good. But more generally, like lidars work by like you often have like a fast rotating thing that is shooting out lots of lasers in different directions. And you're measuring time of flight. You're measuring like how long does it take to hit something and come back, right? And so what makes these things really cool is like the number of light beams that you're shooting out. And they're like pretty high fidelity. So for instance, like Waymo and these companies will use LiDARs to deal with like rough conditions and so on where RGB may not work. Right? So cameras may not work, but LiDARs will work better. And so things like helicopters or cars, etc., will use some version of LiDAR typically. Right? So we're going to use a really simple 2D LiDAR. So in most cases, 3D LiDAR, you shoot it in different directions. In our case, it's going to be a 2D LiDAR. Right? Yeah.
This is really similar to sonar, so why wouldn't we just use sonar?
I think LiDAR is typically a little more accurate for these kinds of autonomous vehicle applications. And it's been like it's faster.
I understand it's faster, but like what, like not diffuse to, say you were in a rainy environment.
Yeah, I guess the other thing that's tricky about autonomous vehicles is there's lots of ambient sound. Right. And so like in an underwater system where you often use sonar, there's not as much ambient sound. Whereas in like in India, for instance, in Bangalore, I don't think any sonar is going to do anything reasonable. And so your sensors become like kind of like they have a lot of interference. And so it can be tough. Yeah. Okay. So similarly to our motion model, our sensor model has to be probabilistic because our sensor model is going to be inaccurate. There's going to be lots of different interference in your sensors. You're going to have incomplete maps. You're going to have people moving around, pedestrians, transparent objects, right? So your sensors are often really noisy, often more than your motion models even. And so your sensor models also have to be probabilistic. So what we're going to do today is we're going to try and define like a reasonable sensor model for LiDAR that you're going to use in your project, right? So you really don't want a sensor model to be confident because it like assigns really high likelihoods to things that are completely infeasible, right? So LiDAR is generally pretty precise, but we're going to try and get a model of P of ZT given XT given a particular map, right? So for now, we're not going to assume that the map is being figured out on the fly. We're going to assume that you know the map. You just need to figure out where you are in the map. Right? There's methods that also try to do P of ZT given M given XT, right? And those are like what you call SLAM methods, but those are slightly different, right? But we're going to try and assume that we like know the map, right? And so we're going to try and build a model of like what is P of ZT going to be given XT and M. Now I said we're going to use a LiDAR. A LiDAR is going to shoot multiple beams in multiple directions, right? So like each of those is going to be one of your Z's. So you're going to have like K different readings for different LiDAR, right? So like your LiDAR will shoot beams and like each of these beams is going to be one of your Z's. Right? And so what you want to get is P of like the joint of all of these Z's given XT and your map. Yeah. Now, the assumption you're going to make in LiDAR or in this motion model for LiDAR is that you're going to assume all the beams are independent. Right? So you're going to assume that these things are independent. If you remember how independence works, if you have P of X and Y given Z, you're going to write as P of X given Z and P of Y given Z, right? Just conditional independence. And so you're saying that your beams are independent. Now, this will make computation easier. You don't have to model every effect, but like, what is the risk of assuming things are independent?
I guess nothing is true.
Nothing is truly independent, that's true. But yeah, I guess like in most environments, you might have one laser beam bouncing off, interfering with another. And so the risk of assuming independence when you are not actually independent is you double count things, right? And so if you're like, saying things are independent, but they're not, then you're like going to get the same phenomenon reading through two sensors and you will double count them, right? And so that leads to this overconfidence. But in general, this independence assumption makes for a reasonable model as long as your LiDAR is spaced out enough. Okay, so our assumption is going to be conditional independence. And so we're just going to try and model what happens for a single beam. And then we're just going to say for multi-beam, it's just the product of a bunch of single beam readings, right? So we're just going to say you shot out a single beam in one direction. What is the measurement? What is the like the measurement is going to be like a distance, right? And you're going to say, what is the likelihood of a measurement given you're at a particular state and you had a particular map? And for many things, you're just going to multiply them together. Yeah. So in homework, all you're going to do is take the single beam model and multiply them together for all the beams. Okay. So what we're going to try and do in the next 8 minutes is try to define what is a single beam sensor model. So how do we have a model for a single beam of light which shoots and hits something and come back, right? So let's say you're given the map, right? And so you knew the distance, you knew this was your position, and you knew this was like the nearest obstacle in a particular direction. So you kind of know what like the true distance is, right? So you know what the true distance is. What we're going to try and do is we're going to say you're never going to get the true distance. You'll get some distribution around it. We're going to try and define the different causes of error and show how they can build a reasonable model. And so all that we're going to try and do in the next few sections is try to say what are the causes of error that you could have, and how does that build a probabilistic model of what you might see in reality. Okay. So for instance, you might have 4 types of errors, right? The first is you might have just some noise around the correct distance. So like let's say your distance was 10 meters, you might get like 9.5. So you might get something which is like in a small range around the correct distance. The second thing that could happen is that there's objects that show up in your environment that weren't accounted for in the map, like someone just walks around, right? So you might have unexpected objects. The third is that you might have a sensor failure. So if you shoot something at like a absorbing object, your light beam never comes back, right? Even though it's like supposed to, it doesn't come back. And the last is that, sensors are weird. They have like random noise. They have failures. And so you might have some degree of random measurements because of hardware error, right? And so we're going to account for these 4 types of stochasticity. There'll be others, but those are the ones we're going to account for, right? Are there others that y'all can think of? Like why else might a sensor, why else might a LiDAR, which is just shooting a beam of light at something, coming back, why might it be not so good?
We don't model so the angle of the robot.
Right. So what we're going to do is we're going to assume that the LiDAR is fixed with respect to the robot. So for each light beam, we're going to choose a particular angle to send it at. But yeah.
What surface is the?
Sorry?
What is the surface?
What is the surface? Yeah. So like, for instance, for like scattering surfaces, you might hit something and it like scatters everywhere, and that may not be modeled. It's like kind of an add-on, maybe like environmental conditions. Environmental conditions, like you have like a aerosol in the air, it might affect your time of flight, yeah. or might bounce things off. Yeah. So all of those things are valid, right? But hopefully this model works reasonably well. So let's try to look at the 4 different factors of noise. The first is just saying that like assume that let's call our true distance ZTK star, right? And so we're going to say around the true distance ZTK star, you're going to have a little bit of a Gaussian, right? So you're going to have a Gaussian, which is like centered around ZTK star with some variance, right? So you're just going to say there's going to be some Gaussian noise around the true measurement. So that's the first source of noise, just because of like local measurement error. And the only thing you have to be careful about is that you like don't want to go above the maximum limit. So let's say your ZTK star was here. You have to like truncate your Gaussian. You like cannot predict things beyond the maximum range, right? And so you're gonna have it be Gaussian, unless it's at the like limit, right? And so you're just going to put a bit of Gaussian around the true. Okay, so ZTK star is what the true thing is, and then you're going to add some noise to it. The second thing you're going to do is you're going to say you might have an unexpected object. So someone might show up in front of your robot, and so you'll get a shorter measurement than you actually have in the map. And so the likelihood of that, we're going to model as an exponential distribution. So it's going to be a distribution that is more likely for shorter distances and less likely for longer distances. Right? And so the logic behind it is that you, for a measurement to happen with the unexpected object, there has to be like no obstacle. Like let's say your obstacle was here. To get this measurement, you have to have no obstacle anywhere before this, right? So in order to get this reading, there has to be no obstacle here, no obstacle here, no obstacle here, right? And the likelihood of there being no obstacle becomes lower and lower and lower the further you go away, because you have to like have, it's like when you're flipping a coin, it's like you have to get all tails, right? So you have to say no obstacle here, no obstacle here, no obstacle here. And so you have to multiply all of these probabilities. And so it's going to be an exponentially reducing distribution, right? And so the second factor is that when you have an unexpected object, you're going to get measurements with a likelihood which is exponential. So it's going to be high for short measurements and then exponentially reduce, right? So you're just going to like reduce exponentially till the object. That's it, right? And so you're not going to, unexpected objects will not be detected if they're behind the object, right? If they're behind the object, you bounce back on your current object. It doesn't matter what's behind you. Okay, so that's the second source of measurement error. So the first one is just some Gaussian noise. Oh, no. Your first one is just some Gaussian noise, and your second one is exponentially reducing. Right? So in your homework, we're not going to do exponential. We're going to make your life easier. We're just going to make it linear. Right? So it's just something that reduces from a short distance, like the likelihood of an unexpected object being close is higher than it being far. Yeah.
Like, so in our final track, will we also just have like some degree of variance? in
Yes.
Tracks. Like,
Yeah.
some people have like good.
There might be there may or may not be a surprise obstacle. Anything could happen. We might have some grad students running around. It's hard to say. Okay, the third type of failure is a failure where a beam doesn't come back. So you shoot a beam at something and it doesn't come back. Let's say you have a absorbing surface or something like that. In that case, you're going to have the beam going to the maximum limit with some likelihood. Right? And so it's a sensor failure. And then the fourth type of error is just random measurements, right? So you might have your hardware fault out. So you're going to have, with some likelihood, you're going to have like a uniform distribution over the whole range of measurements that you could have, right? And so we're going to have these four types of error, and we're going to try and put them together into a measurement model, right? So if everything was perfect, your car was here, and your obstacle was here, this was D, you just have a distribution which is a 100% likelihood of giving you distance D, right? But that's not reality. And so you normally have like some distribution which is like that, right? And that distribution is a combination of these four sources of error. The first is some local noise. The second is some unexpected objects. The third is that you just have a sensor failure. And the fourth is you just have some uniform randomness, right? And so you put those four things together, you normalize it so it's a proper probability distribution, and then you get your sensor model, right? So all of these are like somewhat heuristic. We kind of made them up, but they seem to work reasonably well in practice. Yeah.
Figure out that it's
So if you know the map, right, then you just do like nearest distance to an obstacle. So we're assuming that the map is known. And so if you know the map, you know the nearest distance to an obstacle, but your sensors are noisy and you're trying to model the noise. Right? So the way you're going to compute it in homework 1 or homework 2 is you're just going to measure the distance in a particular direction. Okay, so the distribution looks something like this, exactly like I drew before. And we're going to try and use this to instantiate our homework, right? So overall, we're just going to take each of these for a single beam measurement, multiply them across all the beams, and that's going to give you the likelihood of a measurement given a particular state, right? So that's going to be your observation model. Let's skip these things and Your localization project is going to be the kinematic motion model we talked about. You integrate the physics, add some noise, and you're going to have this observation model with these 4 sources of noise. And your job is to kind of implement both of these things in Python. Okay, so few logistics. Monday is going to be a holiday. Unless you really want me to teach, I can, but I don't think I'm allowed to. And we'll have class on Wednesday. We'll cover particle filters. I have to be in Boston on Friday, but I'll do a remote lecture on Friday. So would you all prefer Zoom or come here and cast? Zoom better? Okay, I mean, so what we'll do is we'll have an option if you want to come here and listen, but you can also do it on Zoom. So yeah, hopefully that's okay. On next Friday. Next Friday, yeah. So I'll see you all Wednesday. We can go. Cool, thank you.
I think they are.